Hello class, Gilbert Fonseca here, your TA. Today I will be talking about simple and fractional distillation. In our previous lab, we performed crystallization, which is a purification technique for a solid compound. We purified benzoic acid, which is a solid at room temperature. But crystallization is not applicable for compounds that are liquid. Distillation is a physical process to separate a liquid from a mixture of liquids. The process exploits the difference in relative volatility of components in a mixture of liquids. Distillation is heavily utilized in different industries. For example, in beverage industries, distillation is used to make wine or beer, and in petroleum industries, distillation is used to make gasoline or diesel. Basically, distillation employs the differences in boiling points of liquids. So even though distillation is quite a simple process, the calculations behind the process require quite a bit of computations. So make sure you read the book in its entirety to at least get introduced to a lot of the math that you can perform and the graphing of several different characteristics, right? So this is the setup for simple distillation. It has three major components. And the first part on your left, lower left here, is boiling a liquid mixture. We usually employ a round bottom flask, one that can fit nicely into the heating mantle here. And then you have a three-way adapter here. It guides the vapor coming out of here, and it enters here. And then the second part is condensing that vapor. So as you're heating this liquid mixture, the vapor comes in and into the right. And here in the condenser, there's water, there's room temperature water or cold water coming in here. It fills the chamber here and then it comes out. So that it keeps the walls in this apparatus colder than here, for example, and the vapor therefore condenses into a liquid and it falls here into the graduated cylinder. And that's the third part, is the collection. Sometimes you can have a graduated cylinder. Sometimes you want to have another round bottom flask. But if you do that, if you're going to seal this entry with your collection chamber, there has to be some sort of opening so that air can come out. That's because you don't want to build too much pressure because there's still vapors pushing, right? Pushing through the condenser. So then pressure can build up here and you'll be in trouble. So yes, it's quite simple. It's called simple distillation for a reason. And fractional distillation coming up is not that difficult either. So simple distillation, it cannot separate a mixture of liquids with close boiling points. It effectively works only when the mixture of liquids have boiling points differ more than 25 degrees Celsius. For example, a mixture of methanol and water. Mixtures that have very similar mixtures whose components have very similar boiling points are often called azeotropes. An example of an azeotrope could be, for example, ethanol and water. Ethanol has a slightly higher boiling point than methanol, but it's sufficient. The increase is enough so that sometimes it's difficult to separate water and ethanol with simple distillation. So using the example of methanol and water mixture, we can understand how the simple distillation can separate the components. You take the methanol and water mixture in a round bottom flask. Here, you gradually heat the mixture. So often you want to get close to the boiling point of the first one, methanol, and then gradually increase around it. So note, methanol has a much lower boiling point than water. So first, at around 65 degrees Celsius, around, it's a key component because, well, it's a key thing to note because heating is always going to have irregularities, especially with more complicated setups. Sometimes you have a thermometer which is far away from the heating source, right? So even though the mantle might give you a temperature, the thermometer might give you another. So you always want to keep these approximations in mind, and always note them in your lab notebook, right? So methanol will start converting to methanol vapor around that temperature, which will be channeled via the three-way adapter towards the condenser. In the condenser, the methanol vapor will be condensed, it will turn into liquid, and be collected here in whatever collecting chamber you have. If you continue to heat the round bottom flask around 100 degrees Celsius, liquid water will be converted into water vapor. So at this point, you want to probably change your collecting chamber so that now you can collect the other liquid, the other component of the liquid mixture. So yes, here it condenses back into liquid water, and you can collect this water in another graduate cylinder. This is the fractional distillation setup. It is essentially the same as the simple distillation setup, except that it differs from the fractionating column. Some columns are very specialized, and they're fitted with carborundum strands in here, but basically all of these have something in the middle, which we'll explain later, that create many mini simple distillations here. But yes, you have your round bottom flask, you have the three-way adapter, you have a thermometer, and a condenser in which water flows in and out. Simple distillation cannot separate a mixture of liquids with close boiling points, but fractional distillation can separate several azeotropes. Fractional distillation essentially is several rounds of simple distillation. In fractional distillation, the vapors pass through the fractionating column before entering into the condenser to cool and to be collected in the collection flask. It essentially purifies whatever you're feeding that fractionating column. So this is a good image that shows it. Methanol and ethanol have very similar boiling points, but as it's entering the fractionating column at a 50-50 ratio, the methanol, which has the lower vapor boiling point, it starts increasing in concentration as you go up the fractionating column, because there's several rounds of simple distillation. So it's like climbing, I guess, and it's purifying the higher you go up because of the rounds of simple distillation. Each condensation vaporization cycle will yield a pure mixture of methanol and eventually yield pure methanol. There's several problems though with fractional distillation. Sometimes the vapors can get stuck over in the downside of each platform. You can read about it in your book, but there's of course ways to circumvent those inefficiencies. The fractionating column contains hundreds of obstacles inside the column to restrict a smooth passage for the vapors. The vapors hit the obstacles and they condensate to liquid. So it'll hit it'll collect in these platforms before being heated again by the vapors rising. The condensate inside the column continues to be heated by the rising vapors, thus vaporizing once more. Therefore, the vapors undergo a repetitive condensation vaporization cycles inside of the fractionating column. Each condensation will yield a pure solution. Make sure you know Raoult's law, especially when you're drawing your graphs. This is what you would do in the laboratory. You would first connect you would set up this portion, and you would add this last, the round bottom flask you added last. You want to grease these joints. You get a paper towel and you put a little bit of grease and then cover these so that they won't get stuck. You fit the thermometer adapter and attach the thermometer, and you would clamp all of this setup first. And depending on what your collection chamber is, you would clamp that as well. You would add 10 milliliters of methanol and 10 milliliters of water and boiling chips. Do not forget the boiling chips. They're very important. Without them, a lot of times pressure can build up dangerously and make your system explode. Unless the process has very little liquid, in which case nothing would really happen because the boiling chips also help boiling in the boiling process. The heating mantle, it must be connected on top of this ring clamp so that you can lower it or raise it depending on what your needs are. In cases of uncontrollable vigorous boiling, you can drop the heating mantle and just stop the boiling. The heating mantle, you connect it to a transformer, and which essentially works as the alternator for the current. For fractional distillation, you do the same. You clamp this, and then you're also going to clamp the fractionating column, but you're going to put copper wool inside of it. The copper wool works as that multi-step ladder that will collect liquid essentially in the little filaments of the copper wool. It's kind of rudimentary, but I mean, this is just a teaching lab, so this is what you would do. You would not use any sophisticated equipment. Keep in mind that the methanol and the water are in a 1-to-1 ratio. That's important for your graph taking, right? Probably in the quiz too. They'll ask you a question related to the ratio and to think about how would the graph look differently for fractional distillation and for simple distillation. So make sure you investigate it in the book or just ask me. Just send me an email, right? Let's move on. Some extra pointers for actually carrying out each of the distillations. Make sure you have cold water circulation in the west condenser, or just in the condenser. The water should go in through the lower outlet, come out of the condenser through the upper outlet. Think about why. I'm not going to give the answer here. You should email me so we can discuss this. It'll probably be in the quiz. Just a heads up. Dial 250 in the transformer. If you need more heat, you would change it, of course. Make sure to turn on the switch of the heating mantle and monitor the inside of the mantle whether it is getting hot. It is okay to touch the inside of the heating mantle to get a feel whether it's working. Notice that the vapor is rising from the liquid that is in the round bottom flask, and it is now channeled via three-way adapter. You would see the vapors like touching the glass, and then you essentially can see them touching and then rising and then touching and then rising. That way you see that it's working. The vapor will be condensed inside the west condenser, and you will notice that the liquid is coming out of the end of the condenser. Make sure to collect the liquid in your collecting chamber. You will collect the first 10 mLs and transfer the liquid, which is going to be mostly methanol or just methanol, to a small beaker, and then use the same measuring cylinder to collect the next 9 milliliters. If you're using a round bottom flask, you would collect whatever you think is around 10 ml and then measure it and then adjust depending accordingly, right? You may not notice a pause in distillation after you have collected the first 9 to 10 ml liquid because the next liquid is water, which needs much higher temperature, right? So that's why you want to keep track of your temperature. you want to avoid superheating, which is bound to occur either way, but you want to avoid it. It says do not bone dry your round bottom flask, but again, it depends on your collection chamber, right? Always try to keep everything a little bit wet, so that there isn't a buildup of gas in wherever the glassware is, right? The most important part of the experiment is the data collection. During the distillation, you will be making this table. You will capture the temperature as you're collecting the distillate. The distillate is the one that is coming out in the graduated cylinder. So think about what's happening, right? So let me draw a sort of a graph. So this would be the volume of the distillate, and this would be the temperature. So as the temperature is increasing, the volume of the distillate will remain essentially the same until it hits a specific boiling point for methanol, right? So it'll be like, steady, and then it'll rise, and then it'll stop again. Say this is methanol, right? The first one would be methanol, and then it would do the same for water. Please discuss with me the graphing that you would have to do. Send me an email about it and we can discuss. You can read about the different kinds of graphs that you can make in the book. And this waste and chemicals disposal is wrong. The liquids, it'll be liquid waste that you have to dispose of, right? Think about where you have to put those wastes. Again, you can email me to try to figure it out with me, because it'll probably be in the quiz as well. That's all. Thank you very much for listening. Hope you learned something. Bye bye.